Hey yo, what's up guys? Baby Bear 4812, almost forgot my name there. Coming at you one more time. Today we're doing Minesweeper. That's problem number 529 on Leetcode. It's got a handful of downvotes, but Facebook, Uber, Amazon, Microsoft, and Bloomberg all like it. So by extension, we gotta like it as well. This one's kind of nostalgic for the rest of you who were also geeks growing up and spent a lot of hours playing this game on the old Windows devices. So bit of a trip down memory lane with this one. I think it's a pretty good problem. I don't think it's turn my fan off. I don't think that it's particularly obvious with respect to how to solve it. So we'll do our best to make it as understandable as possible. Just a heads up, I'm not going to be going over the rules of Minesweeper right now. I'll just kind of assume you know them. If you don't, look them up first, come on right back. Just with respect to brevity of the video, I don't want it to kind of go way too long. Essentially, we're told that we're given a 2D character matrix representing the board. Now, M represents an unrevealed mine, E is an unrevealed empty square, B is a revealed blank square that has no adjacent mines. And adjacent in this problem means all of the 8 squares around it. So up, down, left, right, and then the diagonals, okay? Digits 1 to 8 represent how many mines are adjacent to the revealed square, and X represents a revealed mine. Essentially, you can go through and kind of read this, but what it's saying is this: we're given a board and we're given a click. So somebody has clicked on a specific square. We need to now say, what is the result of that click? Is the game over? Are squares revealed? If so, what did they look like, and how far do they branch out? We're not playing through the whole game. We're not doing anything like that. Just one step. All right. It says if a mine is revealed, then the game is over, and we're going to change the M to an X. If an empty square with no adjacent mines is revealed, then we have to change the revealed blank to a B, and all of its adjacent unrevealed squares should be revealed recursively, okay? This is gonna be where the heavy lifting is, if you can tell already. Third rule says if an empty square has at least one adjacent mine, we will simply change it to a digit, 1 to 8, which represents the number of adjacent mines to that square. We return the board when no more squares will be revealed. Fine. So what I've done is I've taken the liberty of kind of pasting out these letters over here, what everything means, just so you have them as reference. Now, usually when I solve these problems, I like to think about the different ways to go about them. I'll be honest, I kind of see only one legitimate way to go through it, so that's the one I'm going to be talking about. And the way we want to think about it is this. There are basically 3 conditions we got to think about. The first condition is if we click on, so if, let's say board X, Y is equal to an M. So if we click on a mine, and I'll say let X, Y equal to click. What we're given as an input is an actual set of coordinates. And the reason I haven't walked through this example is because I'll whiteboard it with you guys, okay? But we're given a click that's 3, 0. So, click is some sort of array, click with 2 components. I'll call them X and Y. Now, basically, if we click on an M, we want to change board of X, Y. We want to change it to an X and return. That's it. That's all we want to do. So that's like our best case scenario. Otherwise, if we don't click on an M and we click on an E, which is again an unrevealed empty square. If we click on an E, then one of 2 things can happen. So, one of 2 things can happen. One is either we click on a cell that has adjacent lines. So, if board, X, Y has adjacent mines, I'll say change board of X, Y to num of mines adjacent. So again, I'm just walking through the logic, just kind of a bit of pseudocode. We want to say that if we click on a mine, change that M to an X, and it's game over. If we click on a cell or a square that's adjacent to a mine or multiple mines, we want to change that to exactly how many are adjacent. So maybe you're already thinking like we got to get a helper function going, something that'll do a quick search of the surrounding area. Which is where you want your head to be going. Again, that's kind of an easy scenario because we don't need to recurse and kind of check all these other blank squares. Where things get a bit messy is if it doesn't have any adjacent lines. So maybe I'll say else if board X, Y has no adjacent lines. Okay. The reason this one is not fun is as follows. What we're gonna need to do is we're gonna need to change board of X, Y to B. After we change it to B, right, so B represents the revealed blank square, we are now going to have to recursively call all the surrounding cells and check those to see if those are blank or if they have mines around them. So then we're going to be jumping back into this if statement, because we're never actually going to end up hitting a mine. We'll only hit other unrevealed, or eventually revealed blank squares, or squares that have mines adjacent to them. So then we're gonna have to go in and recursively call this and perpetually kind of like jump in this loop of spreading to get to ultimately when we're done. I'm trying to figure out the best way to explain this. To keep finding all of either the blank ones or the squares that surround a mine. Okay. Let's walk through an example on the whiteboard. This is just the big picture logic, and that's really all we're going to be doing. The code will be a touch more involved, but let's jump into the whiteboarding just really quickly to see what this will look like eventually. So in the example that we were given, we are told that the click is at 3,0. Okay, the click is at 3,0, meaning that the click starts right here. So what we're going to want to do is this. And I'll pull out. I think I'll use blue here for the blank ones. We ask ourselves, when I click on this, first off, is it an M? Is it a mine? No, it's not. Since it's not a mine, we check all of the surrounding quadrant, or not even the quadrant, but the eight cells surrounding it, are any of those mines. Since they are not, I'm going to change this to B. So I've got a blank here. And now I need to recursively check all three of these to see if they're going to be a B or they're going to be a digit, right? Because it kind of spreads out, again, as per the original Minecraft rules. Recursively, what's going to happen is we're going to end up checking above us first. So I'm going to check up here and say, okay, well, this is empty, okay? And we check all those surrounding cells, and all of them are empty as well. They're all E, none of them are M. So we make this a B, okay? And we start recursing. Again, we're gonna recurse here, same thing. We're gonna recurse here, exact same thing. When we get to this point, we're gonna realize we can't check our diagonal, we can't check up, we can't check our other diagonal, but we sure can check right. So we end up checking right. When we check right, we realize that, as I'm checking the potentially up to 8 cells around me, there is one mine in the vicinity. So this will not be a B, this will become a 1. And I'll go to red for here. This will become a 1, representing the fact that there's one mine in the direct vicinity of this cell, okay? So we essentially then, we change that to a 1, and as per logic, once we change it to a 1, we're done. We're not gonna get into any more recursion. So we're not gonna be recursing from there. We pop that off the stack and we're sitting back here. Now we're gonna check this bottom right one, which will, again, it'll turn into a 1 because in the vicinity of all 8 squares surrounding it, there is one mine, okay? So that will become a 1. At this point, we've checked all the possible directions for, this is kind of my 8 directions. So we're popping that one off the call stack, and we get down to here. We've tried to check here, and we'll build an error checking to make sure we're out of bounds and all that. I've kind of assumed that we'll do that. We've almost checked everything, except we have this one here as well. Once I get to this cell, I'll realize, okay, this one has to be a 1 as well, because I will do an adjacent search of all the 8 cells around me. Again, once I do that, we're all good there. We get to this bottom one right here now, because that's the next check we're doing in the call stack. This one is going to be blue, right? So I'm gonna go back here. This one is gonna end up being a B, a blue B, and we're gonna continue on going this way through our recursive call. Eventually, what will end up happening is we'll have something like this. So in this specific instance, all of these are going to be 1s, and I believe that actually what we're gonna do is we're gonna have this entire grid will be populated with blanks, apart from this one right over here. The reason we're never gonna get to this one is because the rest of these cells will all be surrounding the mine. And so remember, if we end up placing a digit on one of these empty cells, we are not going to jump into recursive call and kind of dive through all the surrounding cells. We're just going to realize, okay, there is some number of mines here, and I'm going to, or excuse me, there's some number of mines adjacent to me, adjacent meaning in all 8 directions. And so I'm just going to change my value from an E to be the number of mines in my vicinity. That's it. I'm not reaching, I'm not diving in like we are when we hit a blank space with no additional mines like we're doing here. So I hope that makes sense. I tried to do that kind of as quickly but thoroughly as possible, so we're not, like, we don't spend too much time and really make it overkill on the explanation itself. I think this makes sense at this point. Again, if it doesn't, as always, let me know down below. I'm happy to elaborate on it. But I think that at this point, we're ready to dive into the code and see what the implementation will look like. So, okay, let's look at the code. What we're gonna wanna do is as follows. We are basically saying, again, I'll presume here for now that we do get some sort of a legitimate board. If we, or you know what, forget it. If not board, we want to return board, I guess. We'll just return it as an empty board, whatever we're given. Now, what we want to do is to say, well, we're going to want to have an X and a Y value based on this click. And we want from that XY value, we want to decide how we need to go about expanding this board based on these conditions here. So what I'll do is I'll set X and Y equal to click. And again, that'll just extract and destructure the array that we're given. Now, what we're essentially doing is as follows. We're now basically just writing out these if statements over here. And we're telling ourselves this: if board of x, y is equal to n, we're happy, because all we gotta do is say board x, y is equal to x. So we're sending it to x, and that's it. At the end of this, we're gonna wanna return the board. So as I was saying, otherwise, if we haven't clicked on a mine, we gotta start doing some other stuff. We gotta basically figure out, are there any mines that surround me? Okay, so maybe I'll call I'll call it num mines is equal to self dot get adjacent mines. We'll write a function for this, and there we're gonna pass in our board, our x and our y. Now, what we gotta do is say, if there are mines around me, cool, let's change that to a digit, and we're good. Otherwise, then we gotta do our whole recursive call thing. So if num mines, basically if it's greater than 0, this is gonna return a truthy value. Then we say board of x, y. Is not just equal to the number of mines, but rather in our output, you can see that we are, and maybe I'll move this over. In our output, you can see that we've got to return it as a string. So what I'll do is I'll wrap that around and say str, so we return it as a string. Okay, again, nothing too fun here just yet. Although I should say maybe before we go on, let's actually write this function, because you will need to do that in an interview. So we'll define our function as get adjacent mines, self, board, x, and y all go in here. So we'll say number of mines equals 0 by default, and we're going to want to return number of mines. And now we got to check all 8 corners, or all adjacent cells for mines. Now, a couple ways to do this. I'm laughing because the first time I did it, I actually did a manual check of every single one of the 8. So I said, check up and left, check up and right, check right, and so on and so forth. This will work. It's verbose. It looks a bit silly. There's a better way to do it. Don't embarrass yourself like I did, all right? So if we really think about it, I've kind of drawn this up here as reference for you guys, but we can basically look at this and realize that to go from left to right, we are going from y minus 1 to y plus 1 inclusive. And to go from top down, we're going from x minus 1 to x plus 1 inclusive. So we can kind of wrap all that in a nested for loop to check all 8 corners. And what we can do for that is to say, for some row in the range of x minus 1 to x, I'll say x plus 2 because we want x plus 1 inclusive. And we'll do something similar for the columns in the range of y minus 1 to y plus 2 inclusive. Now, if we land on a mine, so maybe we'll say something like if board of RC is equal to mine, then cool, then we'll add number of mines plus 1. However, we also need to take into account the fact that we may go out of bounds here, right? When we're checking our size, we may be checking out of bounds. So we need to make sure that we are in bounds as we're doing all this. To check that we are in bounds, what does that mean? That means that apart from this, maybe I'll move this down for just 1 second so it doesn't get in the way. Right needs to be, the row, excuse me, not right, the row needs to be greater than or equal to 0. And the row needs to be less than the length of the board. And the column needs to be greater than or equal to 0. And the column needs to be less than the length of the board at the row, so number of columns, okay? And if all that stuff is true, so if we're actually in bounds, then we also need to check if that inbound is a mine. If it is, if we're in bounds and there's a mine, then we add number of mines plus 1. At the end of this, we just return the number of mines, and there's our little helper function to tell us whether or not we have any mines around this. So we get that. If there are mines, cool, we change it to the number of mines as a string. Otherwise, this is where the fun begins. Otherwise, we've essentially got to do the following. We've got to say, first off, board of xy has to be equal to blank, right? Has to be equal to b. Cool. But what we also need to do is now check all the adjacent sides around us and decide with them whether they're also blank, i.e. this, or they have mines around them, i.e. this. Since we're going to be self-referencing this whole function, this whole thing becomes recursive, and this is where the fun begins. So, like I said, we're going to use a similar logic to like we used here. So we need to loop through all the adjacent cells around us. So what I'll do is I'll copy paste this, just reduce, reuse, recycle. And from here, I'm going to check every single one of these. Okay, so what I'm going to do is I'll call self.update board, and we'll do board, R and C. So, I'll delete this space here a bit. So what happens here? At this point, I'm actually going to go in, and I'm really, more than anything, I'm simulating another click. We jump into here, if we click, for example, like right here, we click on this little cell, and this cell doesn't have any mines around it, right? So it essentially simulates a click to everything adjacent to it. And everything adjacent to it that doesn't have any mines also simulates a click to those adjacent cells that don't have any mines around it. And that's the key thing in understanding this. We are re-simulating clicks. You're initially given one click. There's it right here. You're given one click, and that click may be sufficient. That click will be sufficient if this is true or if this is true. However, that click will not be sufficient if we're in this case. And that's how we need to loop through and go through it again. Now that we're simulating this click, we're jumping back into here. When we jump back into here, you'll notice that, well, we could arrive at the same issue. Like, what if R and C are not actually valid? So what you can do is as follows. You can essentially say, you can build into this error checking over here, so fine, if not board. Or if any of these pointers are out of bounds. Or actually, you know what, as I'm kind of saying this, maybe it would make more sense to do that here. So let's try to do that here. I'm sorry, I don't want to complicate things, but you know, maybe we'll say, I think, like I said, if we actually borrow any of these, so these are the conditions for being in bounds, and we want to make sure if this is the case, and that board of R, C, if it's not equal to a blank. We don't actually want to jump back on a blank because this isn't really going to help us. We've already checked the blanks, right? So we want to make sure that we're in bounds and that we're not going to be looking at a blank. And if we do that, we're then going to jump into this recursive stack or we're going to jump into this recursive call and start building our recursive stack as we go in order to search all the other blank squares around us. And quite frankly, that's it. I'm looking at this. I know this was a bit of a longer problem. I do want to run this and just make sure that there weren't any errors. So I'm going to go ahead and do that here. So as always, there were errors, and self.update board RC. It's not happy with me. Okay, so it's not happy because the click is actually an array, right? So what I'll have to do is I'll say R and C just like that. And let's see if that works. It does. I'm going to submit it. And there we go. All right, so This was a bit of a longer explanation. I think it was a bit of a longer question that kind of needs answering. There were a couple of specific errors to check and inbounds, and I don't think this is the easiest question in the world. I really don't. Go through it again if any of it didn't make sense. If you're still confused, I mean, drop the questions down below as always. I'm happy to elaborate. This is pretty much the optimal solution you're going to get. And I hope that if you guys get it in your interview, you're going to be able to crush it. You're going to get your dream job, and we all party together. All right? So see you guys next time. Peace.